Hello, my name is Donovan Gray, and this is my Lab 6 Magnetic Molasses lab report. For the introduction, I'll explain the purpose of this lab, and it's to demonstrate Faraday's law, which is one of the four Maxwell equations, and it relates the change in magnetic flux through a surface to an induced E field whose closed path integral provides an EMF, which then induces a current in that closed path if it coincides with conducting material, of course. And it's demonstrated using a falling magnet and conductive tube of aluminum foil. The real-life experiment saw an average time to exit the quarter-meter tube of aluminum foil of 1.098 seconds, and the computational model, which demonstrates the effects digitally, resulted in 0.271 seconds to exit the tube. And the natural free fall speed is around 0.235 seconds for an object falling through a tube that is 0.25 meters long. And so definitely both the computational and real life experiments demonstrate successful eddy currents in both real life and the computational model, which then oppose the motion of the magnet, which is why it falls slower. So here are the relevant equations for this experiment. Of course, we have Faraday's law written in two different separate ways on the left and right side, and then the dipole equation for a magnetic field, the general equation in the middle. On the left side is saying EMF is equal to the negative derivative, time derivative of the flux, magnetic flux, and then on the right side we have the path integral, closed path integral of E dotted with dl is equal to the negative derivative of the flux of B through the surface. So the experimental setup we have is a tube wrapped with conducting aluminum foil, and we drop the magnet into free fall from the top into the tube, and we recorded a video so we could properly determine when the magnet entered and exited, so we can properly measure how much time it was inside the tube. And we held it close to the entrance so we could know that free fall began right when it entered the tube, because we held it too high up, then it had a lot of velocity going into the tube, and the results might be a little bit skewed. And we repeated the trial multiple times to make sure that we could reduce error as much as possible. So here's a bit of the code. It uses the starter code given inputting our proper magnetic dipole based on the magnet we got and based on earlier experimentation to deduce what that number was, and then also using the proper measurements of how much aluminum foil we wrapped around the tube, the length of the tube, and the mass of the magnet. And we inputted the equation for Faraday's law, the equation for the magnetic dipole, and then also the equation for gravity. And the computational model in the end actually shows in real time the magnet falling down the tube and the velocity versus time graph. So here's the modeling graph here. It shows the end of it, so where that blue line there is, that's where the magnet is at the end of the trial, which makes sense because it's at the bottom, of course. And the graph shows the velocity versus time graph of the falling magnet. And it took 0.271 seconds to fall, and like I said, the free fall time is 0.235 seconds. So it did demonstrate some level of understanding of Faraday's law and how that reduces the time it takes for the magnet to fall through the tube. So in conclusion, the computational model made use of the B field equation as well as Faraday's law to represent the effects of the induced circular currents had on the falling magnet. And in both experimental and computational examples, the magnet was slowed to some degree. The effects, of course, were more drastically seen in the real-life experiment, and that makes sense because in the real-life experiment, it's not separate rings that are shown in the computational model. It's a solid aluminum foil, which means that there's essentially infinitely many tiny rings of length D or of width DL, and that continuity helps demonstrate the effect to a greater extent. However, both still demonstrated some, understanding of what happens when you drop a magnet through a conducting tube. And for the what if questions, what if the resistivity of the conductor were reduced as close as possible to zero? Well, if the resistivity approaches zero, then the current approaches infinity, since we know that, EMF over R equals I. And so if R is really, really small, that makes I really, really big. And that means the opposing dipole moment induced in the circular rings of the current would also approach infinity. So essentially, it would fall slower and slower, and once it basically got to, you wouldn't even be able to put it into the tube, since the opposing repulsive force would be so great that gravity couldn't even overcome it enough to even push it into the tube, right? At any moment where the magnet moves at all, the induced current in the rings is so great that the force on the magnet is so great that it can't even fall through. And if holes or slots were cut into the tube, then the opposite happens, right? Because it only applies, the Faraday's law only applies for closed loops. And if you cut a hole in the loop, then there's no longer a complete circuit and the current cannot run through there to oppose the magnetic dipole, right? And as current flows, it creates its own dipole, but that dipole is opposite, and that's why it opposes it and puts a force on it.